Ever wonder how your phone can take a blurry photo and instantly snap it into sharp focus? We tap a filter, and it happens in a fraction of a second. But behind that glass screen is a massive mathematical traffic jam. To see why this is so difficult for a computer, we have to look at how it actually views a photograph. Normally, a computer operates in the spatial domain. The spatial domain is a giant, rigid grid where every single square is a specific pixel, and each pixel has a precise number assigned to its brightness and color. If you want to blur or color shift that image, the computer has to recalculate the numbers for every single pixel by looking at all of its immediate neighbors. Across a standard 12-megapixel smartphone photo, that means doing tens of millions of tiny, exhausting calculations. It is slow, heavy work. But engineers found a brilliant shortcut. Instead of treating the photo as a rigid grid of squares, they translate the image into a landscape of waves. This perspective is called the frequency domain. Think of it like a piece of music. Just as a song is built from low bass tones and high-pitched cymbal crashes, an image is built from visual waves. The wide, slow waves give us the broad shapes and colors, the low frequencies. The tight, jagged waves create the sharp edges and fine details, the high frequencies. Moving from a rigid pixel grid to a landscape of visual ripples provides a direct route to faster calculations. These mathematical tools let us edit the entire picture at once, rather than grinding through it pixel by agonizing pixel. To understand why those wave tools are so powerful, let's think about a tool you likely use all the time, the audio equalizer on a car stereo or music app. If a song has too much screechy treble, you don't manually rewrite the digital audio code for every single second of sound. You just reach over and pull down the high-frequency volume slider. We apply this same equalizer logic to photographs. If a picture has too much visual noise, we don't recalculate the grid. Those harsh details are simply high-frequency visual waves. Trying to smooth out that noise directly in the normal pixel grid requires a punishing, calculation-heavy process called convolution. Convolution is a mathematical operation where a computer must compare every single pixel against its neighbors to calculate a new value, a process that must be repeated millions of times for every frame. But by translating the image into a collection of frequencies, we get to treat the photo exactly like a song. We skip the exhausting math of convolution and simply turn down the volume on the visual treble. The link between sound waves and digital images is rooted in a specific mathematical theorem. This incredible discovery changed computer science forever by giving machines a way to process visual data exponentially faster. On this slide, the top integral, g of u, represents transforming our image into the wave world. Your processor skips the intimidating calculus in the middle, jumping straight to the shortcut at the bottom. Convolution in the spatial domain equals multiplication in the frequency domain. In plain English, the agonizing process of blending millions of pixels together is mathematically identical to just taking thing F and multiplying it by thing H once we are in the wave world. This specific equation is the ultimate digital shortcut. It takes operations that once required massive mainframe computers and turns them into a simple multiplication problem. So every digital picture you see lives a double life. It is a rigid grid of pixels, and it is a rich, layered collection of waves. Editing those pixels directly forces computers to do heavy lifting, but editing the waves requires almost no effort at all. This abstract mathematical trick is the unseen engine making our modern digital experiences possible. It is the reason complex video games can render massive, detailed worlds in real time without crashing your console. By filtering textures in the frequency domain, the system handles complex lighting and blurring instantly. It's also why your phone camera can process a beautiful, softly blurred portrait mode shot the second you press the shutter, instead of freezing up for 5 minutes. The next time you apply a soft focus filter or blur the background of a video call, remember the math working behind the scenes. You are quite literally turning down the volume on the visual treble. If you could invent a real-life volume knob for anything you see every day, what kind of visual filter would you create? Let me know in the comments below, and don't forget to subscribe.